Related rate problems are really fun to do. My advice to you is to always start by drawing a picture of what's going on. So here we have two airplanes that are heading towards the same airport. So let's call this point here the airport. And then we've got airplane A that is east of the airport right now. And airplane A is flying at a rate of 250 miles per hour. So that's its speed. And again, it's heading towards the airport. Airplane B is heading north towards the airport and it's flying at a speed of 300 miles per hour. Okay, and then what I'm drawing in blue here is the distance between airplane A and airplane B. So let me call that blue dashed line D, where D is the distance, okay, between airplane A and B. Okay, so we know that as time, right, goes on, so we've got a couple of variables here. We've got time, which is t. We've got, let me see here. So we've got time, which is t, measured in hours. What other variable do we have? We have distance. And we have lots of different distances. So we've got d, which is distance between the two airplanes. Okay, and that's measured in miles, right? We also have, let me call this distance here in red, let's call that A, where A is the distance, okay, between airplane A and the airport, okay? And then let me use this purple color, right? Let's let this represent B, which is the distance between airplane B and the airport, okay? And then we know that as time, so this is all with respect to time, so we know that as time goes on, right, and the airplanes are moving closer and closer to the airport, this distance is going to get smaller and smaller. So the distance is decreasing, right, as the airplanes are approaching the airport. Okay, so we've got a couple of other variables as well. We know that if we take the derivative of A with respect to time, that unit is miles per hour, then we have the speed of airplane A, okay? And then same thing, if we take the derivative of B with respect to time, that unit in the numerator is miles, the unit in the denominator is hours. Miles per hour gives me the speed of airplane B. We can also take the derivative of distance with respect to time, where distance is measured in miles and time is measured in hours. So you can see there we've got a rate or speed. So here, this would be the rate. So I'm changing the wording here from speed to rate, but it means the same thing. Is the rate at which the distance between airplane A and B is changing, right? So the rate at which the distance between the two airplanes is changing, and again, with respect to time, okay? And that's what this question is asking us. It's asking us, what is the rate of the distance between the two airplanes, right? And we want to know what that is when airplane A, so we want to know what that is when airplane A is 30 miles east of the airport. So we know A is 30 miles, okay? And airplane B, so we know the distance of B is 40 miles from the airplane. So the only piece of information right now that we don't know is we don't know, well, actually there's two things we don't know. We don't know what the distance, so we don't know what this is in miles. We don't know the distance between the two airplanes as they're getting closer to the airport. And we also don't know the the rate. And again, this is our goal right here. We're trying to figure out what this is, right? Our goal is to figure out what that rate is. We do know what the rate or the speed of airplane A is. We know that that is 250 miles per hour. And we do know that airplane B is traveling at 300 miles per hour. Okay, so in order for us to find D, capital D, dt, we need to do a couple of things, and that is to first figure out what the distance is between the two airplanes when airplane A is 30 miles from the airport and airplane B is 40 miles from the airport. So what we can do here to find D, right, we can use Pythagorean's theorem, because hopefully you can see here that I've got a nice right triangle. And so here I could just use Pythagorean's theorem, which tells me that if I square D, that is equal to the sum of A squared plus B squared. So then D squared is equal to 30 squared plus 40 squared. And then I'm going to go ahead and take the square root of both sides so that I can figure out what D is, not D squared, but D. And so D is equal to the square root of 300 squared is 900. 40 squared is 1600, and then the square root of, so we just found out that the distance between the two airplanes is 50 miles when airplane A is 30 miles from the airport and airplane B is 40 miles from the airport. And for related rate problems, we need a relationship between all of these variables. So using Pythagorean's theorem from before, we know that D squared is equal to the sum of A squared and B squared. And our goal is to find the rate at which the distance is changing. So our goal is to find D, so D, capital D, with respect to time. So we need the derivative. And so guys, here, this is where we're going to take the derivative of this equation. So let's take the derivative of each of these terms in this equation. So I'm going to take the derivative with respect to time of D squared, take the derivative with respect to time of A squared, and take the derivative with respect to time of B squared. So here we're going to be using implicit differentiation. Okay. Now let's go ahead and take the derivative of D squared. So we're going to use the power rule. That's 2 times D to the 2 minus 1 times D, capital D, dt. On the right-hand side, we're doing the same thing. 2 times A to the 2 minus 1 times the derivative of A with respect to time plus 2 times b to the 2 minus 1 times the derivative of b with respect to time, okay? So again, we're using this notation d dt to show that each of these variables, right, when I take the derivative with respect to time, represents the speed of each of those variables. Okay, and so then now I have 2 times d to the first power times d, capital D, dt, and then again, I'm just rewriting these, and I hope you see that I don't need to raise a to the first power. You know that that's to the first power, okay? Plus 2b times db dt. Okay, now remember from the previous slide, we know the values of, right, dA dt and dB dt. We know those values. We also know the value of d, a, and b. They're up here. So what we're going to do now is just use substitution, and then our goal is to then solve, right? Solve for d, capital D dt. All right, let's do the substitution. So when d is 50, right? I don't know what the derivative of the distance is with relationship to time. So let's leave that alone. And then I've got 2 times A, which is 30. And then the rate at which airplane A is flying at a rate of, what was its speed? I already forgot. It was flying at 250 miles per hour, okay, plus 2 times B. So B was 40 miles from the airport, flying at a speed of 300 miles per hour. Okay, And then now let's just multiply this out. So I've got 100 times dt is equal to, let's see here, that's 60 plus 200, or 60 times 250, which is 1500, plus that's 80 times 300, which is 2400. And then we're going to, I'm going to go ahead in this step here, if you guys don't mind, I'm going to divide both sides by 100. Okay, and then that way I can go ahead and solve for d with respect to time. And so in the numerator here, when you add that and divide by 100, you get 390, and because this is a rate, that's miles, so the unit is miles per hour. And because the distance, since distance is decreasing, right, over time, right? Because the two airplanes are getting closer to the airport, that distance d is decreasing. We got to make sure we stick that negative sign there. Okay, so if you leave your answer like this, it's very important that you have the negative sign. But if you're writing out the answer in words, you can leave out the negative sign by replacing that sign with the word decreasing. So you can say the distance, okay, between airplane A and B is decreasing, okay, at a rate of 390 miles per hour when airplane A is 30 miles and airplane B is 40 miles. I'm running out of space here from the airport. Okay, and that's what your answer represents.